So, any questions before I get started? Nope. Okay, let's go to what we were discussing in 1.8. So in 1.7, we learned all these different proof styles and proof techniques. And then in 1.8, we're trying to become a little less rigid and start doing some more interesting proofs. So we discussed case-by-case proofs, or proofs by exhaustion, which are in some sense proofs where you just do it, so to speak. I don't know if I'm legally allowed to say that. But anyways, so I want to do one last example of a interesting case-by-case proof that's in the book, and I hope that it'll be a good warm-up after the weekend. So the question that I'm asking us to think about is, what are the possible last digits last digit? What is the possible last digit of a perfect square? Question mark. And so what we should try to do is figure out what's going on and then try to prove it. Okay, so in a situation when we have a broad open question like this, the first thing that we should do is do a bunch of examples and see what we should expect. So let's just write down a bunch of perfect squares for a little while. 1 squared is equal to 1. 2 squared is equal to 4. 3 squared is equal to 9. 4 squared is equal to 16. Thus far, we've had a whole bunch of different digits. 1, 4, 9, 6. 5 squared is equal to 25. Okay, 5, that's a new last digit. 6 squared is equal to 36. Ah, that one we already have. 7 squared is equal to 49. That one we already have, 9. 8 squared is equal to 64. Ah, 4 we already had. 9 squared is equal to 81. Ah, 1 we already had. 10 squared is equal to 100, a 0. That one's kind of new, but if you thought of 0 as 0 squared, then that one's not new either. So it looks like the collection of last digits that we could have are at least 0, 1, 4, 9, 6, and 5. So we've never seen 8, we've never seen 7, and we've never seen 3, for instance. Okay. At this point, this is just a guess, right? Like, we can't possibly list all of the perfect squares because there are infinitely many perfect squares. So how, does anyone have an idea, either by creativity or by having read in the book, how we approach the proof of this conjecture of ours, that these are precisely the last digits that appear in perfect squares? You can use the last digit of the number that you want to square. I'm not exactly sure what you mean. Could you elaborate? Ah, yes, I now understand what you mean, with no elaboration on your part. Exactly. The idea is that, yes, precisely. The idea is that we can write any number as the following. 10k plus b, where b is either equal to 0 all the way up through 9, right? So this is just like a base 10 expansion where I can always write something as a multiple of 10 plus some number between 0 and 9. Yeah, exactly. So then when we square a number like this, if we square a number like this, 10k plus b squared, This will be equal to 10k plus b times 10k plus b, which is equal to 100k squared plus 10 kb plus 10 kb plus b squared. And we notice that all three of these numbers don't contribute anything to the last digit because they all are multiples of either 10 or 100. Exactly. So the only thing that contributes to the last digit is b squared. And so if you write down, well, what do I want to say? Essentially, this makes it so that this proof can be done by proof by cases. So now we can do proof by cases. In other words, we only need to check things of the form 10k plus 0 squared, 10k plus 1 squared, 10k plus 2 squared, etc., all the way up to 10k plus 9. Oh, you can't see that. 10k plus 9 squared. So essentially, the clever part of this proof, or the idea of this proof, is that even though there are an infinite number of things to check, by a clever use of understanding the problem, we can break down this into finitely many cases that we need to check, because every number is off from a multiple of 10 by 0, 1, 2, 3, all the way up to 9. And so in this case, we get exactly last digit, the exact same list: 0, 1, 4, 9, 6, 5, 6, 9, 4, 1. And so indeed, we see these are the only possible digits that can appear as the last digit. Any questions on this?
So is b squared the last digit? Am I understanding that correctly?
So b squared could take over the last 2 digits, but then we only take the last digit out of it.
Got it.
So these can't possibly contribute to the last digit. This one contributes the last 2 digits, but we don't care about the second to last digit, so we just pick off the last digit. Good question. Any further questions? Okay. So the next thing that I want to go through, I like this material at the end of chapter 8, but I kind of want to go a little quick today because I want to get to sets. Okay, so the next thing that we should do is we should talk about existence proofs. So is there a more formal format we need to put this proof in, or is what I did okay? Yeah, this should be more formal. I didn't write out the full proof of this. The correct way to write this would be to write the proof and first say, notice that any number can be written as 10k plus b. Since the square of 10k plus b is equal to this, then the only term here that contributes to the last digit is the b squared term. Therefore, we check the following cases, and then you'd write out in each of these cases what it is. So one should be a little more formal with this proof by cases thing, but yeah. Okay, so existence proofs, it's a very common thing in mathematics that we want to prove that a certain object exists and possibly that it's unique. So first I want to talk about existence of objects and how we approach these proofs. And there are two kinds of ways of showing existence. One is called constructive, and one is called non-constructive. The constructive ones are more naive in the sense that for a constructive proof, you usually just build the correct object that you need. And we'll see a couple examples of this. Here's an example. Prove that there exists a pair of consecutive integers such that one is a perfect square and one is a perfect cube. What do we do here? Yeah, in this case, if we're trying to prove that there exists a pair of numbers with this property, then all that we need to say is, oh, I can find an example. So proof, consider 8 and 9. 8 is equal to, since 8 is equal to 2 cubed and 9 is equal to 3 squared, these satisfy the conditions. And then I put a little box to say, I have done a formal proof. Right? So this is an example of when you're trying to show that something exists, you just find it, or you just build it, perhaps, is another way to think about it. So this would be a constructive proof of existence. I constructed the thing that was supposed to exist. Is this okay? I think this one's okay. Okay. Here's a much cooler way of proving something. Here's a beautiful example of a non-constructive proof. And this one's an example in the text, so you may have seen this one as well. I'll do one that's not in the text. So non-constructive existence. So show that there exist irrational numbers x and y such that x to the y is rational. Okay, so we only currently know of one irrational number, right? That's my understanding. Currently we know of the irrational number called square root of 2. So we're about to do a non-constructive proof that there exist x and y such that, which are irrational, such that x to the y is rational. So proof. First, let x equal square root of 2 and y equal square root of 2. Then consider x to the y, which is equal to square root of 2 to the square root of 2. What are the two options for this number, whatever it is? It is either rational or irrational. Exactly. This number is either rational or irrational. If it is rational, so now we're into cases. Case 1. If square root of 2 to the square root of 2 is rational, we are done. Right? Because square root of 2 is irrational, square root of 2 is irrational, and then in case square root of 2 to the square root of 2 is rational, okay, then we found what we needed to find. So here's case 2. Square root of 2 to the square root of 2 is irrational. Well, if this is an irrational number, then I can construct a new pair of numbers and let x prime is equal to square root of 2 to the square root of 2. Then consider square root of 2 to the square root of, so consider x prime to the y, which is equal to square root of 2 to the square root of 2 to the square root of 2. What are my power rules? What do I do when I have iterated powers?
Multiply.
I multiply. This is equal to square root of 2 to the square root of 2 times square root of 2. What's the square root of 2 times the square root of 2?
Excuse me, does that say x prime or x to the y?
X prime to the y. So I picked a new number x prime, which is square root of 2 to the square root of 2. And then here, I'm raising x prime to the y. So it's square root of 2 to the square root of 2 to the square root of 2.
Okay, thank you.
Yep, sure. What's the product of square root of 2 times square root of 2? 2, perfect. Square root of 2 squared. But this is just the same thing again. Square root of 2 times square root of 2 is equal to 2. Boom. Thus, if square root of 2 to the square root of 2 is irrational, then square root of 2 to the square root of 2 and square root of 2 work. QED. Okay. My question to you is, do I know which of these two pairs actually works? There are two options, right? Either square root of 2 and square root of 2, or square root of 2 to the square root of 2 and square root of 2. Yes. The key point is I do not know which of these two is the correct pair. I don't know which pair works. But what I do know is if this pair doesn't work, then this pair does. So by works, I mean satisfies the conditions of existence. I need to find a pair of irrational numbers such that x to the y is rational. So what I just showed is that if square root of 2 to the square root of 2 is rational, then this is the correct pair because I have two irrational numbers such that this to the this is rational. And if this pair doesn't work, namely square root of 2 to the square root of 2 is irrational, then I'm allowed to put square root of 2 to the square root of 2 over here because it's irrational. And then I showed square root of 2 to the square root of 2 to the square root of 2 is rational because it's just 2. I agree. This is an excellent proof. Any further questions about this one?
How do you figure out which one works?
I never do, but I know one of them must.
So if we were asked like how we figured this out, would we say we used a constructive method or a non-constructive method? It would be non-constructive.
Right. This is non-constructive because I haven't actually produced for you the pair x and y such that x is irrational, y is irrational, and x to the y is rational.
Okay, I see.
But I do know that one of these two must work, so I know that such a thing exists. Either this works or it doesn't, and if this doesn't work, then this one does. And of course, this one doesn't work if square root of 2 to the square root of 2 is rational, because then it doesn't satisfy the conditions of both x and y being rational or being irrational, right? This one is kind of tricky, and it is very different from our constructive proof of existence. So I want to give a little more time for people to process and ask me a question if you have a question.
I have a question for x prime. What was the reasoning for choosing square root of 2, the square root of 2?
So in this case, the reason that square root of 2 to the square root of 2 is chosen is because it ends up working. So I would say that this is a clever proof that requires some creativity to come up with square root of 2 to the square root of 2. Are you asking why it works, or
No,
how
no.
one would?
Yeah. Why did you choose it, or how did you know to choose it?
Yeah.
What
In
you
this
knew?
case, this was creativity on whoever thought up this proof.
Got it.
Yeah. Do we know which is right, like mathematically? I would guess that we may actually not know mathematically which is correct. Let me think. I definitely know that there are tricks like this with related numbers like e and pi, where we don't know mathematically whether e times pi or e to the pi is not transcendental. For this one, I'm not sure whether this is actually known, but we have proven the statement already. So in a certain sense, it doesn't matter for the sake of this proof. I could probably pull that off by the end of class, probably without discussion. But we're not going to get to what numbers are transcendental or not in this course. Any other questions? Let's do another example. This one's easier to kind of see. Show that the product of two of the following is non-negative. Um, 65 to the 1000 minus 8 to the 2001. Did I give this for homework? Plus 3 to the 177. 79 to the 1212 minus 9 to the 2399 plus 2 to the 2001, and 24 to the 4493 minus 5 to the 8192 plus 7 to the 1777. Okay. I have three ridiculous numbers here. And what you're being asked to prove is that the product of some pair of them has to be non-negative. How do we go about this?
We're going to use the non-constructive one, definitely.
Definitely going to be non-constructive. A hint is that these numbers don't matter at all. You have negative numbers and positive numbers. I mean, I don't actually know whether I have negative numbers and positive numbers. I mean, you're right, though, that we can break down into a number of cases about whether these numbers are positive or negative. So what are the cases that I could consider? What are the possible cases if I have 3 numbers? Well, one is they could all be non-negative. All 3 are non-negative numbers. Right? This is the first case. The second case is 1 negative number. I could have 2 negative numbers. Or I could have all 3 negative numbers. Exactly. Y'all are getting the idea. I don't actually need to pay attention to any of these numbers to break it down into these 3 cases. Case 1, if all 3 numbers are non-negative, any pair multiplies to be non-negative. Case 2, if there's 1 negative number, well, non-negative means that it could be 0, right? So technically the 3 options that we have are positive, 0, or negative. And what I'm doing is I'm lumping in 0 with the positives. And we still have this nice property that a non-negative number times a non-negative number remains a non-negative number, right? Because if I multiply 0 by 0, I still get 0, which is non-negative. And if I multiply 0 by a positive number, then it is also 0, which is still non-negative. So case 2, 1 number is negative. The product of the other 2 will be non-negative. Case 3, 2 numbers are negative. Their product will be positive, right? Because a negative number times a negative number is positive. And then case 4, all 3 are negative. The product of any pair is positive. Oh, you can't see. Okay. And that's the box. So the point is, this is a non-constructive proof because what this problem was asking for was to show the existence of a pair inside this tuple, this 3, such that the product is non-negative. I didn't actually construct the pair. I cannot tell you which of these 2 will multiply together and give me something positive because I have no idea what these numbers are. But I can produce for you a non-constructive proof that there must exist some pair which multiplies to be non-negative by examining all the possible cases. So this is another example of a non-constructive proof of existence. Any question here? No response. Okay, that's great. I'm going to press on in that case. We have 20 minutes to get to sets. We're going to get to sets today. Actually, that's very exciting. I want to mention one last thing. So sometimes we want to show not just existence, but existence and uniqueness. So I want to do at least an example of an existence and a uniqueness proof. So let's do the following. Prove that if A, B, and C are real numbers with A non-zero, then there exists a real solution, or there exists a unique, QUE solution to AX plus B is equal to C. Proof. So usually when we want to prove both existence and uniqueness, what we should do is we should first prove that something exists, and then as a second step of the proof, show that it's unique. So how do we show that a solution exists?
Wouldn't we just solve for x?
Yeah, let's solve for x. We can find a solution by solving for x. Namely, x is equal to c minus b over a. Since a is non-zero, x is a real number. Phenomenal. Not only have we proven existence, we've actually constructed the number that does the trick, right? This is a constructive proof because the answer to what is the root or what is the solution of this equation is c minus b over a. Great. This is constructive. Now, the second step is to show that it's unique. To show uniqueness, essentially we've already kind of shown it's unique because there's only one solution to this equation, namely we got it by solving for x. Since this is the only solution which appears when we solve for x, it is unique. QUE, unique. This is kind of a wimpy uniqueness proof though, because you don't really get to see what's going on. And things might be more interesting if I had a quadratic polynomial, right? Then you could factor using the quadratic formula, and then there would be two possible solutions, right? So what I want to do is I want to give you a further idea about how to go about uniqueness proofs. Oh, so technically I'll put a little box here. Box. Here's just kind of a technique or a tip for proving uniqueness. Technique or tip for proving uniqueness. So we already have our solution, namely, so a solution is x is equal to c minus b over a, right? So one way to think about showing uniqueness is to try to modify x by some other number and show that that other number has to be 0 in order for it to be a solution. So for instance, let's consider another solution to ax plus b is equal to c of the form c minus b over a plus k for k a real number, right? So here what I'm doing is I'm saying, is it possible that I can add some real number to my solution and get another solution, right? Perhaps there is another solution of this form, right? And I can write any real number in this way. So then we check. Then a times c minus b over a plus k plus b is equal to c, right? Because this is supposed to be a solution. And we see that so the a's will cancel. So I'll get c minus b plus a times k plus b is equal to c. And then I'll cancel. Then canceling, I'm going to cancel a c from both sides by subtracting, and then the negative b and the b will cancel. We get a times k is equal to 0. Since a is not equal to 0 by assumption, what do we conclude?
That k equals 0.
K is equal to 0. Exactly. So what I did is I tried to build a new solution by taking my old solution and adding something, right? Maybe I can find a new solution by adding some real number to my previous solution. And then what you check is that if you want to build a new solution in that fashion, then the thing that you added had to be 0, right? This is a cool strategy or way of thinking about proving something is unique. You say, well, I produce another one that should look like this, and then I show, well, k had to be 0 all along, so I was actually just working with the same old solution, c minus b over a. Thus, c minus b over a is the unique solution. How do we know what new solution form to propose? Couldn't we try infinitely many solution forms? It's possible that you could try infinitely many solution forms, but notice that any real number will be of this form, right? Because c minus b over a is a real number, and k I'm letting be an arbitrary real number. So I can get to any real number by taking this fixed real number and adding some other real number, right? So something of this form where I'm letting k be free is already like trying all possible real numbers. Does that make sense? Right, but you're absolutely correct in that for more difficult problems, it could be quite challenging to figure out what is the correct perturbation, so to speak, to do. And that's where some cleverness comes in. Yeah. So in this case, this is sufficient, but as you go further and further in math, there will be some cleverness in this choice of thing. And so that's still a very good question that you asked, Shreya. Any other questions?
Why is there an A outside of the parentheses?
So what I did here is I just rewrote ax plus b is equal to c. But with my new hypothesized solution, which is of the form c minus b over a plus k. So essentially what I'm saying is I'm trying to find a new solution to this equation, Namely, if I plug this number in for x, then this equation is satisfied. And then I just checked what that would force. So here all I did was I plugged in this new solution in for x.
I see.
And then after doing some arithmetic, I discovered that if this is a solution, then k has to be 0. Namely, I'm back at the original solution that we started with. Kind of cool, huh? Any further questions? Oh, I'm going to put a little box here because I'm done with the proof. No? No further questions? Everyone is
Where's
comfortable?
my burn?
Okay. If everyone is comfortable, then I would like to say congratulations. We are done with chapter 1. And we're moving on to, there is a question. So in proving uniqueness, do we need to do this part, or can we stop at, since this is the only solution? I haven't really done a great job of showing you how to prove uniqueness in problems. What should I do? Here's a brief example of a slightly more challenging example. So let's assume that we have ax squared plus bx plus c is equal to 0. Show that there are at most two solutions. So something that you could do here is that you could use the quadratic formula, and then this would break out to be x minus 2 real solutions. Yeah, this should be 2 real solutions. There will always be exactly 2 solutions over the complexes, but currently we're working over the reals. So here we'll have x minus, what is it? Negative b plus or minus the square root of b squared minus 4ac all over 2a. And then x minus negative b. Well, here this is a plus and here it'll be a minus. Minus square root of b squared minus 4ac all over 2a. So here, as long as these are real numbers, then you've produced 2 solutions. And what you could try to do in this case is you could take this solution, say, to show that there are no further solutions. What you could do is you could say, assume there's a solution of the form negative b plus square root of b squared minus 4ac all over 2a plus k. And then what you'll find is that if you do the math from here and you plug this solution back in for x, then you'll find that k has to be whatever the correct thing is, such that this number plus k gives you the other solution. And then this would be a way of showing that you have precisely 2 real solutions, as long as this one's a real number. I hope that that helps as a kind of sketch of a more complicated example of how I use this technique. Essentially, you pick one. As long as you have one, then you say, okay, I'm gonna like vary, or I'm gonna perturb this solution, and then you check what are the possible values that work for your perturbation, and it turns out that the only other values are the ones that you already found. There can't be any third solution. So here, k will have to be equal to either 0 or whatever k needs to be, such that this plus k is equal to this. yeah, kind of sketchy, but I'm just trying to illustrate how this idea is used to prove uniqueness. Okay, in the remaining 4 minutes, we're going to start with sets. I should mention briefly, in chapter 2, here are the things that you should read and here are the things that you should not read. If you feel like reading ahead. The sections that we will cover are the following. We will cover 2.1, 2.2, 2.3, not 2.4. We will cover 2.5 and not 2.6. So don't read 2.4 or 2.6 because we won't cover them. Okay, in my pithy remaining time, let's get started with chapter 2. Sets. Let's start with a definition. This is kind of a weak definition, but a set is an unordered collection of objects called elements or members. A set contains its elements. We write A in A to denote that little a is a member of set A, and say B is not in A to show that B is not a member of set A. So what I will almost always do is I will write little letters for elements and capital letters for sets. But of course, at some point in this class, we're going to be talking about sets containing sets. So things will eventually get muddy. But for the beginning, and as much as I can, I'll usually use lowercase for elements of a set and uppercase for the set containing those elements. Okay, for finite sets, we can just write down all the elements. For instance, and when I write sets in this fashion, I'll use these braces. So for instance, here's a set that contains some numbers, 2, 4, 6, and 8. Here's a set whose members are 2, 4, 6, and 8. I could also write a set, for instance, the set A of people in this class. I could write this out in terms of bracket notation and write down all of your names, but I can also write down a set by there are other ways of describing a set besides just listing all of its elements, of course, because many sets are infinite. So we could also use set builder notation. So for instance, I could also write this set, let's call this set A. A is also equal to the set of x in z, namely integers. This line is such that 0 is less than x, which is less than 10, and x is even. Oh yeah, you can't see what I'm writing. Okay, so this is called set builder notation. Here you specify the domain. So essentially what I'm writing here is I'm writing a subset of the integers. So this is kind of the overarching domain where I'm taking elements from. This line is such that, and then here I put conditions. So namely, I want the collection of integers such that x is an even integer, it's greater than 0, and it's less than 10. These are the same set because they have precisely the same elements. I know that we're going kind of crazily through here and that time is up, but is this okay so far? Any questions? Well, if there are no questions, then I hope everyone has a wonderful Monday and a wonderful week.
Thank you.
Yep,
Thank you.
thank you all.
I just want to check your office hours is in like 10 minutes, right?
Like 20. It's at 10:30.
Oh, okay. See you then.
See you then. And it'll be with the same Zoom number. So
All right. Thank
see you
you.
shortly.